A power station can produce enough electricity for a city, but many power stations cannot start without electricity from somewhere else. So if an entire grid goes dark, what starts the first machine? At 2 a.m., imagine every transmission line on this map is dark. Not one neighborhood, not one city. The connected system has lost its electrical heartbeat. The obvious solution sounds simple. Start a power station. But a large generator is not a giant battery waiting behind a switch. Before its turbine can deliver electricity, the plant may need pumps to move fuel or water, fans to control combustion, lubrication systems to protect bearings, cooling equipment, control computers, switchgear, communications, and safety systems. Those house loads normally take power from the grid. In a total shutdown, the grid they depend on is the thing that has disappeared. That is the dead grid paradox. The first generator needs electricity before it can make electricity. Operators solve it with a capability called black start, now often described more broadly as electricity system restoration. A black start resource can establish power without relying on the surrounding transmission system. It might use an on-site diesel generator, a battery, a hydro unit, or another self-starting arrangement to wake its own essential equipment. But starting that first machine is only the first move. The grid cannot be restored by reconnecting every customer at once. Generation and demand have to remain matched from the first small load to the final synchronized network. Add too much demand and frequency falls. Energize the wrong path and voltage can move outside safe limits. Connect two electrical islands before their waveforms align, and protective equipment may trip them apart. This is why restoration is planned, tested, and rehearsed long before an emergency. NERC requires transmission operators with this responsibility to maintain coordinated restoration plans, identify black start resources and their characteristics, document cranking paths, define acceptable voltage and frequency limits, and prepare for conditions that differ from the studied plan. The first goal is not to light every home. It is to create one stable electrical foothold that can start the next machine. The restoration sequence begins with assessment, not motion. Operators need to know which lines, substations, generators, communications links, and protection systems are actually available. A blackout may have damaged equipment, separated regions, or left conditions that no training simulation predicted. A switching action that is safe on an intact network may be dangerous on an uncertain one. Once a viable starting point is confirmed, the black start resource supplies its own station service. Controls wake up. Lubrication and cooling begin. Fuel or water systems are prepared. The turbine comes to speed, and the generator establishes a usable voltage and frequency. Now there is electricity, but only inside a tiny controlled boundary. The next challenge is to move that power outward. Operators energize selected transformers and transmission lines to form what restoration plans call a cranking path. This is not simply the shortest route to another plant. Every line and transformer changes the electrical behavior of the island. A lightly loaded transmission line can raise voltage. Transformers draw magnetizing current when energized. Motors and pumps can demand a large burst at startup. The island is small, so each change matters more than it would on a healthy continental grid. At the far end of the cranking path sits a larger generator that cannot start by itself. The new island provides that plant station power. Its pumps, controls, cooling, and other auxiliaries come alive. Then the larger unit can synchronize to the island and add generating capacity. Capacity creates room for carefully selected demand. Operators may restore loads that stabilize generator output, power critical facilities, or support the next step in the plan. They do not treat every megawatt of demand as interchangeable. A hospital, a water pumping station, a communications site, an industrial motor, and thousands of household appliances affect both priorities and system behavior differently. All the while, operators regulate two quantities viewers rarely notice when electricity is normal. Frequency reveals the moment-to-moment balance between mechanical input and electrical demand. Voltage has to remain within limits as lines, transformers, generators, and loads are added. If frequency or voltage moves too far, protective relays can disconnect equipment and erase hard-won progress. Meanwhile, other restoration teams may be building separate islands from different black start resources. Those islands cannot simply be joined because they are both producing electricity. Their frequency, voltage, and phase angle must be close enough for a controlled synchronization. Picture two waves moving 60 times per second in North America or 50 times per second across much of Europe. Closing a breaker when those waves disagree can create damaging currents and torque. Operators adjust the islands until the conditions align, then close the tie. Two fragile systems become one stronger system. The same logic repeats. Establish a source, energize a path, start more generation, add chosen load, stabilize, and connect. The U.S. Department of Energy describes restoration progressing from damage assessment and black start units through energized islands, and finally the integration of those islands into one interconnection. The important detail is that recovery is not a smooth animation. Each step is conditional. Equipment may fail to respond. Communications may be limited. Fuel, weather, staffing, cyber systems, or damaged lines may force operators away from the preferred route. NERC therefore requires professional judgment when actual conditions do not match the studied conditions. The plan provides structure, but people still have to read the living system in front of them. That is why a black start resource is more than a generator with a starter motor. It is part of a coordinated chain of tested equipment, trained crews, resilient communications, switching orders, operating limits, and agreements between organizations. The hidden system is the choreography. For decades, restoration plans were built around a relatively small number of large, controllable power stations. That architecture is changing. Retiring thermal plants, expanding wind and solar, batteries, microgrids, distributed generation, and high-voltage direct current links create new possibilities, but they also change the physics and coordination problem. NESO's Distributed Restart project demonstrated a bottom-up approach in which distributed energy resources can help build local restoration zones and support the transmission system. That does not mean an ordinary rooftop solar array automatically keeps operating during a blackout. Many grid-connected inverters are designed to disconnect when the grid disappears, protecting workers and equipment. A restoration resource needs the controls, communications, protection, testing, and contractual role required to operate an island safely. The distinction matters because having energy available is not the same as having a system that can establish and regulate a grid. Batteries and grid-forming inverters can respond quickly and may support black start, while hydro units can offer self-starting capability and sustained mechanical generation where suitable. Other plants may provide large blocks of power once a cranking path reaches them. No single technology eliminates the sequence. The emerging opportunity is a more diverse set of anchors and more ways to restore from the bottom up as well as the top down. But diversity creates dependencies of its own. A distributed restoration zone may rely on communications and automation across equipment owned by several organizations. PNNL's work on black start trends highlights challenges involving inverter-based resources, communications, cybersecurity, testing, and the changing generation fleet. Resilience, therefore, cannot be measured only by installed megawatts. Operators need to know which resources can establish voltage, control frequency, survive islanded operation, energize equipment, communicate during a widespread outage, and repeat the performance in a test. This changes how we should think about a blackout. The dramatic moment is the failure, but the deeper infrastructure story is preparation. Restoration capability is purchased, engineered, modeled, tested, staffed, and coordinated even if it is never used at national scale. Its value is similar to a fire escape. Success is partly the absence of the event and partly knowing that a verified path exists if normal systems fail. When the grid comes back, the visible result is a light switching on. Behind it is a chain that began with emergency power inside one dark plant, grew into an island, reached another generator, accepted load without losing balance, synchronized with neighboring islands, and finally became a network again. The grid does not restart itself. People restart it by assembling stability one controlled decision at a time. The next time power returns after a major outage, the first light you see is the end of a much longer sequence. Somewhere, operators verified a path, started a source, balanced an island, and connected it to something larger. If you want another hidden system traced from failure to recovery, choose the next investigation: the GPS timing signal that synchronizes critical infrastructure, or the water towers that keep pressure at your tap when demand changes. Subscribe for the system behind the switch.